In the last lecture, we were looking at the last part of learning theory that was left behind after the spring break. And in this, the motivating question for all of this was the theory that we saw before was all about finite concept classes, and the complexity parameter that was important was the size log of the size of the hypothesis space or the concept class. And this tends to be rather useless if the size of the hypothesis space is infinite, which is the case that happens, say, for instance, with, say, linear classifiers. So we're building up this theory to discover a complexity parameter that behaves like the log of the size of the hypothesis class. And along the way, I defined something called shattering. I'm not going to go over the examples again, but I just want to revisit the definition. Shattering is a property of a hypothesis space, H, and a hypothesis space is nothing but a set of functions H, and a finite set of examples. And we say that the hypothesis space shatters the set of examples if, no matter how you label the examples as positive or negative, there is one function in this hypothesis space that can match that labeling. Okay, and we saw some examples of this. By the way, just to kind of dot some I's and cross some T's, when I say set of functions, I mean functions that predict a plus or a minus, binary classifier. And when I say label examples, once again, we are labeling examples as plus or minus. So the intuition here is if a function class can shatter a large set of points, then it contains, it is in some sense more expressive. We are using this notion of shattering to measure, in some sense, the expressiveness of sets of functions. And through the last lecture, we saw that for left bounded intervals, so basically things that look like this. So I have a here, and everything in this region is a plus, and everything here is minus. This function class, and changing the A gives you different functions, right? This function class can shatter 1 point, but it cannot shatter 2 points. On the other hand, open intervals, or just intervals, which are defined by 2 numbers, and everything in between is plus, everything outside is minus. This can shatter 1 point, this can shatter 2 points, but it cannot shatter 3 points. And the counterexample, the way you prove that it cannot shatter 3 points is you consider any 3 points, and all you need to do is find one labeling of these 3 points for which no function, no value of A and B can agree with it. So if I put a minus here and a plus here and a plus here, this cannot be matched. If even one labeling cannot be matched, we declare that 3 points are not, cannot be shattered. And then we looked at linear classifiers in 2 dimensions, and any set of 1 point can be shattered. If you have a point, if it's a plus, I put a line on this side. If it's a minus, I just reverse the direction of the line. So 1 point can be shattered. Any 2 points can be shattered because if you, no matter how you label these as plus or minus, I can find a line that puts only the pluses on one side and the minuses on the other. For 3 points, it turns out these 3 points cannot be shattered because if I put a minus here and a plus here and a plus here, this can. So those 3 collinear points cannot be shattered because you cannot draw a line that puts the minuses and the plus on one side each. But there are sets of 3 points that can be shattered because no matter how you label these 3 points, it works. However, when it comes to 4 points, no matter how 4 points are laid out on a plane, they cannot be shattered. So 4 points where 3 of them are a line and the 4th one is outside is basically like this set here. So it doesn't work. 4 points where that form like essentially like a rectangle cannot be shattered because you just label the two vertices as plus and 2 of them, the opposite vertices as minus, and you can't shatter that. And 4 points where The fourth one lies inside the triangle, cannot be shattered. So there are three cases inside this. No matter how 4 points are laid out, it cannot be shattered. So in general, 4 points cannot be shattered. Okay, this is roughly where we left things off at the end of the last lecture. Any questions about any of these things? Yes.
Does that get down to having 5, 6, 7?
Well, if 4 cannot be shattered, 5 cannot. Because if 4, consider any set of 5 points. Inside that set is a set of 4 points, right? And you do the same, you play the same game. So if 4 cannot be shattered, 5 cannot be shattered, so we are done. Once we get to a point where it cannot be shattered, we don't need to go beyond. Yes.
So in the case of a rectangle, can you draw a line through the plus, you can say, divide on this line?
But that's a different function class. The function class we are considering is, it's a half space. So it has to be, if you can't just say on the line. Yeah.
The reason that we have 3 cases is that covers all possibilities that are range 4 points, right?
Yes, that's right.
How do we know that?
Well, I just proved it to you. Either 3, the way to think about that is, let's call these cases A, B, C. Either, if you have 4 points, and here I'm making the argument, I'm not going to write it. If you have 4 points, either 3 of them lie on a line, or no 3 of them lie on a line. Right? Those are the only 2 possibilities. If 3 of them lie on a line, we are in case A. If no 3 of them lie on a line, of course, 2 points are going to lie on a line by definition. So if no 3 of them lie on a line, then either the 4th point, let me go back. If no 3 of them lie on a line, 3 of them form a triangle. Now we have the 4th point. So let me draw the triangle. 3 of them form a triangle. Either the 4th point lies inside, in which case we get to C, or the 4th point lies outside, in which case we get to B. These are the only possibilities. So this is a bit of a creative argument, and for each sort of VC diamond shattering proof, you may have to come up with such an argument. Other questions? Yes.
So when it comes to 4 points, since it's not able to be shattered for any set of examples, that just means that we can't shatter 4 at all, right?
We cannot shatter any set of 4 points. Yes.
We have to specify that. So since we only have when we have a set of 3, that one can be shattered in certain cases. So for that one, we say it's shattered for it's able to be shattered with this set, but not that set. That's what 4 we can write. It's not able to be shattered for any set.
Yes. Eventually, what we'll get to with VC dimensions is it's enough if we can find one configuration of the points that can be shattered. Then, for a certain definition, we are good. And the other counterexample is no configuration of the points can be shattered. That's all that's going to matter. Yes.
What is the 4th point, which indicates B? The 4th point lies near the class.
It lies. Oh, good. So let me draw that. So I'm going to zoom in here. So we have these 3 points. No, not plus. Minus and minus. And you said the 4th point lies somewhere here. Okay. In that case, what I will do is I will not consider that triangle. I'll just relabel the points. I'll call this plus these 2 minuses. You can always find a triangle the goal is to label the opposite vertices as plus and minus respectively. Does that the idea here is no matter how the points are laid out, I can come up with a labeling. First, the points are provided to me, then I come up with a labeling. No matter how the points are laid out, I can come up with a labeling that cannot be linearly separated. Okay, so that's about shattering, and to go exactly to where we left things off. Turns out some functions are so expressive that they can shatter any number of points. No matter what number of points you give them, they can shatter. And I'll just name an example later on. So intuitively, if you have a function a function class really, if you have a set of functions that can shatter a smaller number of points versus another function class that can shatter a larger number of points, the one that can shatter a larger number of points can agree with more kinds of data sets. Because no matter how the data set is labeled, there's some function that agrees. So your learner might discover that function. So it is more likely that a function class that can shatter more number of points can be consistent with any data set, no matter what the data set. Which is why the larger this leads to the intuition that the number of points that can be shattered by a function class is a measure of its expressiveness or its capacity. I use the word capacity here sometimes. Its capacity to match data sets. The extreme situation where the function class can shatter an infinite number of points, that particular function class is said to be unbiased. It has no, there is no information in the that has gone into the design of that function class that says I prefer these kinds of labelings. Because if had there been any sort of such preference, it would have a limited, it would not shatter an infinite number of points. Yes.
So you say that some functions can shatter infinite points. So can I say that these functions would lead my models to overfit?
Yes, exactly. It can lead your model. I won't say anything with a will, but can. It can lead your model to overfit. Because there might be noise in the data that maybe flips the label. There's still a function that fits that. Okay, I think we are now in a good place to introduce VC dimension. VC dimension is, I guess that's not the goal. Oh, okay. So we have this definition of shattering. Set of examples is shattered by a set of functions if for any way in which the set of examples can be partitioned into plus and minus, there's a function that agrees with that label. The VC dimension of a hypothesis space is simply the size of the largest finite set of points that can be shattered. Concretely, if you have an instance space X, I can consider finite subsets of X. And consider a finite subset of X. A finite subset of X is just a set of points. And I can ask, does my set of functions shatter that set of points? You keep trying that for larger and larger sets of points till you can't. And the largest set of points that can be shattered, the size of that, the number of points is defined to be the VC dimension. This is just a definition. So concretely, all VC dimension proofs have two parts to it. If there is a subset of size D that can be shattered, even one set of points that can be shattered, then VC dimension is at least D. If no set of points of size D can be shattered, then the VC dimension is strictly less than D. So all VC dimension proofs have a lower bound and an upper bound. For linear classifiers, for instance, in 2 dimensions, there's at least one set of 3 points that can be shattered, points lying on a triangle. No set of 4 points can be shattered. So the VC dimension is 3. In fact, we've already proved a bunch of VC dimension results. I'm just going to summarize them. For half intervals, meaning half interval is just you have the everything inside this is positive and everything outside is negative. There is a data set consisting of just 1 point, at least one data set consisting of 1 point that can be shattered. No data set of size 2 can be shattered, so the VC dimension of half intervals is exactly 1. The VC dimension of intervals, an interval looks something like this. You have Everything here is plus and everything on both sides is a minus. The VC dimension of intervals is 2 because any set of 2 points can be shattered. No matter how the 2 points are laid out on this line, I can find an interval that covers only the positives. But no set of 3 points can be shattered because if you have 3 points, I'll call this a minus and this a plus, and you can't find an interval that covers only the pluses. So the VC dimension of an interval is 2. Half spaces on a 2-dimensional plane. In other words, linear classifiers in 2D. There's at least one set of 3 points that can be shattered, and no set of 4 points can be shattered. So the VC dimension of half spaces on a plane is 3. I've been presenting all of these things to you as examples of shattering. In fact, what I've actually presented are VC dimension proofs, because the VC dimension is simply the size of the largest subset of points that can be shattered. So there's a question. If it has to be finite, what is the VC dimension of an unbiased hypothesis space? That's an interesting question. The definition of VC dimension says the size of the largest finite subset that can be shattered. Then I said there are certain function classes that can shatter an infinite number of points. Formally, for those function classes, we say that the VC dimension for any number n or any d, the VC dimension is greater than d. And this is true for every integer d. If it's true for every integer d, then it basically means that the VC dimension is infinite. Does that answer your question? Yes.
The linear classifier critical word kind of relation.
Yes.
Can we say that VC dimension is real?
Yes, because the idea is even one subset is enough. Even if there is one set of points that can be shattered, then the VC dimension is more than that. A few more VC dimensions. We talked about, yes.
What's the half space in the plane?
Half space in a plane is nothing but a linear classifier in 2 dimensions. A half space, and what does a linear classifier do? A linear classifier cuts through the space and says this half is plus and one half is minus. So it basically marks out a half space as a plus.
But then if those 3 points, they are equal defined, how to separate them.
What do you mean?
3 points are in the same, linear in the same line.
Yes,
They have different classes, how to separate.
we can't. We just need one set of 3 points. If we have one set of 3 points, even one data set of size 3, if it can be shattered, then the VC dimension is at least 3. The definition of VC dimension is all we need is one subset, even one subset. And this is something that confuses people a bit the first time you see it. Even one subset of points is enough to, even if one subset of points of a certain size can be shattered, then the VC dimension is the size of that, at least the size of that.
Does not need to shape them.
It does not need to shatter every set of points. Yes. Did you have a question? Okay. No, actually no. No labeling of 4 points can be shattered. Wait. Can you repeat that? Labeling? Good. This is I'm glad you asked that, because this is so let's consider these 4 points. Okay. Let's say I'm going to give this label. And of course, I can separate it.
Yeah.
This is not shattering. This is just separation. Shattering requires every labeling to be matched. So no matter what the labeling is, there must be a classifier. Then we call it, only then does this get shattered. So I'm not going to enumerate all possible labelings here, but there are many of these 16 possible labelings that can be matched. But there are at least 2 that cannot. All we need is 1. So if we can find one labeling of the points that cannot be matched, then this set of points cannot be shattered. And yeah,
This was in there equals as a special case instead.
no, so let me just enumerate all the cases here, okay? And now it's going to get a little bit. Okay, it's going to get a little bit hairy. So let's consider 3 points. With 3 points, I claim some set of 3 points can be shattered. And the key word here is some. There's some set of 3 points that can be shattered. My goal is to prove this claim. If I want to prove it, it doesn't make sense that I will use this set because this cannot be shattered. Instead, I'll use this set. And to prove that this can be shattered, I'm going to enumerate all possible labelings. So I have 3 points. I can label them all as a minus. Okay, I can label them all as a minus. I can label them all as a plus. I can label 2 of them as a plus and 1 as a minus. I can label 2 of them as a minus and 1 as a plus, and these are the only possible cases that exist. And in each case, I can find a linear classifier that separates out the pluses from the minuses. So that's all there is. Some set of 3 points can be shattered. This means that VC is greater than equal to 3. This only shows that VC is more than 3. This still doesn't prove that VC equals 3. To show that VC dimension equals 3, you need to then, so this is the lower bound. This is the lower bound. And then there's the upper bound. And for this, the claim is no set of 4 points can be shattered. And for this, you have to go through that argument, which I made before. And this, if you can prove this, which we can, this means that VC of this set, I'm calling that H, is less than 4. So we proved before that VC is at least 3 and VC is less than 4. VC has to be a number, an integer, which means VC equals 3. So specifically addressing the points that came up, all we need is one set of 3 points to be shattered. There may exist other sets of 3 points that are not shattered, which is okay. All we need is one set of 3 points. When it comes to 4 points, we need to prove that no set of 4 points can be shattered. And here, the definition of shattering is to prove that a set of 4 points cannot be shattered. For every configuration of 4 points, we should be able to find even one counterexample in the form of a labeling. If even one labeling cannot be matched, then that cannot be shattered. So this proof it's worth kind of being super systematic about this proof because every piece of it is easy, but the problem is the combination of for at least one and every for all and there exists, they kind of make this a little bit confusing. Yes.
So for a set of examples, the values of the features for those examples don't change with the labels.
Yes, that's right. The examples are given to you. But for the lower bound, you get to pick the positions of those points because you get to choose which set of points. There's a question on Zoom. To have VC dimension of 5, would the space be able to shatter every configuration of 5 points or at least one? Even one configuration of 5 points would be sufficient. Usually, when people ask me about this in office hours, I tend to write a rather formal looking expression that I'm not going to write now simply because since this is the first time you're seeing it, it can get confusing. But it's worth kind of going back and thinking about how the universal quantifier and the existential quantifier interact with each other in the definition of VC dimension and shattering. Okay, so we have that, but we talk about linear classifiers in 2 dimensions, but linear classifiers can exist in any dimensions. In D dimensions, in general, the VC dimension of a D-dimensional linear classifier is D plus 1. We saw that for 2 dimensions. For 2 dimensions, the VC dimension was 3. Neural networks are interesting. We've not covered neural networks, so we won't go into the details of this. But with neural networks, this is a loose statement because there are many other things that come into play, but VC dimension tends to behave like the number of parameters in the model. A very simple class of functions, which we'll cover at the end of the semester, is called one nearest neighbors. Turns out one nearest neighbor has an infinite VC dimension, which is kind of peculiar because this might be one of the oldest types of machine learning algorithms that exist. Just an interesting sort of a anecdote. If you have a D-dimensional linear classifier, how many parameters does it contain? D plus 1, right? Each feature gets 1 weight, and then there's a bias term. So there's a D plus 1. So the number of for linear classifiers also, the VC dimension behaves like the number of parameters, is the number of parameters. There are other aspects that come into play with neural networks that we've not yet covered them, but I just want to mention it. Turns out learning neural networks is not, training neural networks is not the easiest thing in the world. And optimization factors, you're already facing those in your perceptron, where you're running your classifier learner over multiple epochs over the data. And it just so happens that for perceptron, the initialization does not really matter. But with neural networks, it's possible that the initialization makes a difference. And even though there exists a classifier that perfectly can match a data set, all these optimization issues, which we will discuss, I'm guessing in April, will end up, they add extra complexity to this. After we cover neural networks, you can come back to this lecture and try to prove that the VC dimension of one nearest neighbors is infinite. Kind of a fun proof. Now, let's go back to where we left things off. Why are we even talking about VC dimension? Our goal is to talk about sample complexity. Remember, we talked about Occam's razor and agnostic learning and such things. In both of these, in the finite hypothesis scenario, in all cases, the sample complexity depended on the log of the size of the hypothesis space. Just so happens that the VC dimension behaves like the log of the size of the hypothesis space. And I'm going to present results to you without proof, and you don't have to remember these expressions, but we'll talk about, you need to know the implication of this rather than the actual expressions. Oh, there's a question. No. If you have a consistent learner, what that means is you have a learner that always finds a classifier that perfectly agrees with every label in a data set. So what it does is, given a set of examples, it will find some hypothesis. And this result says, if the number of examples that you have is more than this horrible looking expression, then with probability at least 1 minus delta, the hypothesis will have a error less than epsilon on future examples. And by error, I mean generalization error, of course. Ignore all the constants and stuff. Let's only worry about a few, is this a packed guarantee? For it to be a packed guarantee, we need it to be polynomial in 1 over epsilon, which it is. We need it to be polynomial in 1 over delta, which it is. And if this quantity is a polynomial in the dimensionality, then this expression is a packed box. So if the VC dimension is a polynomial in the dimensionality, then we have a packed carry. For linear classifiers, for example, I just said the VC dimension of a linear classifier is d plus 1. It's linear in the dimensionality, which means a consistent learner operating over the set of linear classifiers is a packed algorithm, is a packed learner. Questions about this? Yes.
This is compensation or infinite hypothesis, yes?
Yes.
If there was an opposite hypothesis, we probably see the other ones because there's going to be
Yep.
bigger.
Yep.
But would this still technically work for non-infinite?
Yes. In fact, the VC dimension of a finite hypothesis class is at most the log of the size of the hypothesis. And that's a homework question. Okay, this is for a consistent learner. I can also do this for the agnostic setting and things get ugly, but basically you have a generalization bound that says the generalization error of the hypothesis is the training error plus this expression that is basically a polynomial in the VC dimension. Once again, we have a polynomial in the VC dimension. It's just a horrible looking polynomial that, I would not expect anyone to remember, but it's a polynomial. It's a polynomial in the VC dimension. It's a polynomial in the delta. And, the idea is that if you have m examples and your training error is this much, your generalization error can be no more than the training error plus that expression. As a exercise, this is, the longer I stare at this, the more answers I get. So let me move on. It's worth thinking about how to compute the VC dimension of function classes. As an example, we saw axis parallel rectangles at the beginning of the lecture, which just says that everything inside the box is positive, everything outside is negative. You can ask what's the VC dimension of axis parallel rectangle. In fact, I did ask that in the homework. So think about how you might go about proving it. Every VC dimension proof has a lower bound and an upper bound. The lower bound just tries to find some configuration of points that can be shattered. The upper bound tries to show that no matter how you configure points in the plane, it cannot be shattered. Okay, this concludes our section on computational learning theory. Let me do a quick recap because this has been a long set of lectures. We started off this unit with pack learning, and I defined pack learning as just a property of a hypothesis space. You need to know what pack learning is. And the key point here is we care about future error, generalization error, and not training error. We considered two different types of hypotheses, the finite case and the infinite case. In the finite hypothesis setting, we drew a connection between the size of the hypothesis space and sample complexity. And you should be able to derive and understand the sample complexity bounds. We should be able to count the number of hypotheses in a hypothesis class. In the infinite hypothesis setting, which is what we looked at now, we had to kind of invent new theory to be able to even get to these bounds. And this involves the definition of shattering and VC dimension. We need to know what they mean. We need to be able to find VC dimensions of simple concept classes like the kinds that we saw in the lecture. And the key point here is higher VC dimension means the sample complexity can be more. Now, stepping back a bit, computational learning theory with pack learning is just one definition of how to define successful learning. There are advances beyond this. A lot of this is from the mid to late 80s, and there has been work since then. But this is sort of a good sort of a starting point to think in those directions. Pack assumes that there is a fixed but possibly unknown distribution that generates examples and builds the theory from there. And one way or another, we keep coming to this idea of Occam's razor. The Occam's razor in the consistent setting, in the agnostic setting, with finite or infinite hypothesis classes, all of them basically say if you make your functions, if you make the set of functions your learner explores more complex, then learning with provable guarantees can be harder. It does not say that having a larger function class means guarantees that learning will fail. Learning can succeed even if your function class is more complex. But but to be able to prove this sort of a fact guarantee, it's better if you have a smaller function class. There are many extensions to this theory. To the case where the data is noisy, the case where the data distributions are known, to the case where the models themselves produce probabilities and not labels. And one sort of an interesting and important extension that we're not going to talk about, but if you're interested, something that you can explore on your own, is something called the fact-based theory, which makes assumptions about distributions over a hypothesis space. A huge caveat about computational learning theory is that we've built all this beautiful math, all this nothing to explain why ChatGPT works. It does not, because the largest neural networks, essentially the largest models that we see in the news today, essentially violate all the assumptions that we baked into place here, and yet they work. What that really means is that there is room for new theory. The empirical machine learning has gone far beyond our theoretical understanding of the field. So those of you who find this sort of stuff exciting and want a challenge, try to prove why these things, why the kinds of neural networks in the machine learning systems that we encounter, we use today, why they work. And you do that, and you'll get fame and glory and a lot of money. Well, fame and glory. This was a picture from OpenAI's technical report that described GPT-4. Statistical learning was all about, let me zoom in so that you can actually see that all these words are now familiar. We see dimension, we've not talked about kernels, but then we'll talk about risk minimization, unbiased, soft margins, and all these things. On the other hand, neural networks are just, anyway, we'll talk about neural networks later. So there's room for more theories. Our understanding is not complete. On the other hand, it does present interesting ways to think about learnability. Before computational learning theory came along, before Valiant's paper on the theory of the learnable, the idea of learnability was too amorphous to mathematically define. And the huge contribution of that paper, for which he got the Turing Award, is to take something that's so human, like the idea of whether something is learnable or not, taking that and converting it into a rigorous mathematical field and building this theory on top. We can already prove that certain types of functions are not learnable even using this. We saw mistake bounds before, and there's an interesting connection between mistake bound learning and fact bounds. Any concept class that can be learned in a mistake bound setting, it turns out there's a theorem that says it can also be learned in the fact setting. So you can prove mistake bounds, and then you get fact learnability for free. It also raises interesting theoretical questions. I'm going to list out two of them here. If a concept class is learnable weakly, that means that you have a learning algorithm that can produce a classifier that is slightly better than chance, but not really great. Can you do something with that? This was a theoretical question, and that's going to be the next topic of our discussion. It directly led to this idea of boosting, and it formalizes the idea of ensemble. Another sort of an interesting extension, interesting outcome of learning theory was we've seen these bounds, right? The generalization error is less than the training error plus some ugly term involving VC dimension. So our goal is to make the generalization error as small as possible. Can we set up an optimization problem that tries to minimize this quantity and as a side effect minimizes this quantity? This idea leads to this notion of the risk minimization principle or the idea of loss minimization, which is basically the bread and butter of modern machine learning. That winds up our section on computational learning theory. Any questions?